Okay, so the problem is simple. I will give the program a set of x and y's, and I want the program to plot an average graph or least error graph through it. It's the thing that we do almost every day in physics in our labs, and I want to do Python program on it. Okay, so the idea came from the machine learning book I was reading, where I saw this formula, and translating it to human languages means that the y predicted value will be the sum of all the variables it depend on multiplied by some coefficients. Now if the coefficients are higher, then it will be more important, and if it's very small, then it will be of less important. So how the equations are solved? A variable r is defined, which is the mean square error, that is the actual value minus the predicted value, and this r is minimized by differentiating this r with different ai's, and these equations are solved for the ai's. So my idea was to use the variables, that is the input variables, as the powers of x, and it becomes a simple Taylor series, as because Taylor series can just fit a lot of functions, so it is the easiest to use. Now while I was doing this, I read another thing, which is lasso. Now lasso in machine learning of scikit-learn is nothing but a L1 regularization. What it does is it tries to fit the values of x and y, and if it sees that some of the variables, some of the powers of x in my case, are not good enough, then it just turns them zero and thereby drops those coefficients. So what I will do, I will just write y predicted as different polynomials of x, sin x, cos x, things like that, 1 by x, 1 by x squared and such, and I would expect that lasso will eliminate the unnecessary part from my equation and predict the correct equation. So let's implement that into our code. So what I need to do is just take a values of x's and y's and turn that to the variables and give that to the program. So we started the program. Now the data function that you are seeing is nothing but taking the values of x's and turning into various things. I am using polynomials of x, fractional polynomials, not separate polynomial, fractional powers of x, and negative powers of x sometimes. Okay, so the first thing while doing this is that we need to define something which will regulate how closely the data needs to go. In lasso, there is something called alpha, which decides how closely the data will follow, and if it's close enough, it will drop something. If it's not, it will keep that variable. We need to regulate this alpha and optimize the alpha to our liking to give the maximum accuracy. And the first thing that I ran into was errors, and you don't need to be surprised. This will be the norm of this video because I will run into lots and lots of errors. So I tried to resolve this error, but I couldn't. So I did what most people do in this case. I started over. Now while I'm starting over, it is a good time to tell you what the while loop here is. So in A, I have defined what is called the test score. That is, I have given some values of x and y's. It has predicted those x and y's, it has trained a model, and now this model is implemented on test values of x and y. Now if a is 1, then it is perfect. Similarly to b, it is a train value, that is the given values, how well it predicts. One can assume that we need the test and train values to as much high as possible, but one thing we need to keep in mind, the train value, that is the b, should never be less than that of a. It is the underfitting, that we have trained less accurately with a trained value and we are predicting more accurately with the test values. Always we need to do is keep the value of b higher than that of a, but we shouldn't keep the a too low. That is, it is very good at train values, but it is very bad at predicting real world values, which is called overfitting. Okay, so the first function is ready and it seems pretty good. So what we need to do is just give new functions and define those things, and we run into some errors. So right now here I'm optimizing things a little bit, trying to see what gives what. Next I wanted to plot the sine and logs, so see how well it goes, and as you can see that sine and log doesn't go well at all. It is very bad. So we need to change something. I noticed a few things in this case, that our data is very low. If I give 5 or 6 points, the curve doesn't know, because I gave almost 24 polynomials and more input variables. The curve doesn't know which one to keep, which one to eliminate, because there are only so many less number of points. So we want to increase more points. Now one might add, wait a minute, what you are trying to do is increase more points. You have given some points, you want to plot a graph from between those points. But what I want to do here is just inaccurately, maybe just increase the number of points between any 2 points, and for that we need interpolation. Now the best approximation in interpolation was Lagrange interpolation. Now it is very good, but the problem with it is that it is a polynomial interpolation. It is nothing but a polynomial series, and if your data isn't polynomial, it takes a little bit time to converge. You can see in the experiment that it does not converge well at all with the x to the power half curve. So Lagrange polynomial is out of the equation. At that moment, one thing dawned on me. How do we plot the curve? When we are drawing the curves by hand, how do we do that? We see the points, that is, we place the points on the graph, and we imaginarily in our mind draw straight lines from one point to another. The last thing we do is draw an approximate curve between that. So what if I gave points lying on those imaginary lines that we draw in our minds between one point and another? What I mean is this. Here I have drawn an average curve of e to the power x, and I have taken some points of e to the power x. I have drawn straight lines joining one point to the other, and I have drawn the actual curve in orange. You can see that the points diverge in this case, and that is also true for log x. But when we are doing experiments, the function is not very accurate to e to the power x. It has some errors, and I can expect that those errors will numb out our situation. And as I said before, I don't need the interpolation to be absolutely perfect. If it was absolutely perfect, I would use that to plot our average graph. Interpolation just provides a few more data, telling the program that the data you are plotting should be close to this one. So I will not give the x and y's into the code, but I will give data on those lines and then translate into x squared, x cube and other functions, and then tell the code to plot an average graph. So I am doing exactly that, and we have got the straight line. So straight line is nothing tough, but when you have got almost 30 to 35 variables, straight line can be tough. We have got the straight line, let's try something else. This is the log of e to the power x minus 1, and it's very good too, but we needed to change the initial value of alphas, or we needed to change the guess value of alpha, and we don't need to do that. The final program should be such that we only need to give x and y, and it should run everything smoothly. Now here is the turning point. I experimented lots and lots and lots on these curves. I even changed the program. I used L2 regularization instead of L1. What I found is this, that my underfitting and overfitting, regulating all those conditions is not necessary at all. All we need to do is take an initial value of alpha and bring the value of alpha down until it satisfies our condition of A being high as much as we want, B being high as much as we want, and the ratio of A and B is not very far away from 1. To be honest, I was heartbroken at this point, because all I wanted to do was use machine learning to do this program, and found out there is a very little bit of machine learning. But on the flip side, I could plot a number of functions using this program. So I tried to perfect this program. I plotted x to the power half and a straight line with negative slope, a random polynomials and such. And finally I perfected the program, and as you can see. Okay, so last thing that I want to say, that since I'm not a coder by myself, I am using the Scikit-Learn library. I don't have a GitHub profile to upload this code. So what I have done is just uploaded my code into my blog. You can check that out in the video description down below, and use the code and give me feedbacks about it. I'd very much like to hear from you guys. Peace, and may the force be with you.